All right, thanks, Joshua. So hi, everyone. So yeah, I've been tasked to essentially give an introduction on neural nets. So a lot of what I'm going to talk about is fairly basic concepts, but those are concepts that you'll be building on for the rest of this week. And I mentioned this just so you're aware of the amount of pressure Aaron has put on me for this talk. So what I'll essentially cover is, basic feed-forward neural net, multi-layer perceptrons. This is another way people describe them. What I'll go through are first talk about essentially, given some input x, how we make predictions using a neural net, where I'll refer to f of x as the output. That is, if you're already somewhat familiar with neural nets, we take an input vector x, and feed-forward neural nets will compute a series of layers of features, which are hidden layers, and then eventually, ultimately, compute an output layer that serves to make a prediction about the label for some input x. And I'll focus mostly on classification during my talk. And so I'll talk about first how you compute all of these units in the neural net, so do forward propagation, talk about the different types of units, activation functions that people tend to use, have a little bit of discussion as to what is the capacity of neural nets and why they're interesting in terms of their ability to model various complicated functions. And then I'll move on to actually talk about, given that we've accepted that this is the type of model, a multi-layer neural net that we want to fit to our data, how do we actually fit it on data? How do we train neural networks? So I'll discuss the type of loss function we use for classification, talk about the backpropagation algorithm, which will allow us to get gradients to perform some gradient-based learning, and describe some of these gradient descent algorithms and a few other tricks of the trades information that you'll need for applying neural nets in practice. And then ultimately, I'll talk a little bit more about motivating the case of deep neural network and talk about some of the more recent advances that have surfaced in the literature and that were sort of inspired by this ambition of trying to learn deeper neural networks. So things like dropout, batch normalization, and unsupervised pre-training.
Is this for your 2 lectures or just this morning?
This is for the 2 lectures, yes. So I am not crazy. So thanks for the sanity check. So in the first part, what I'll do is that I'll cover forward propagation and backpropagation, mainly only computing the gradients. Then I will talk about, then we have lunch, and then after that we'll talk about the complete learning algorithm for fitting a neural net on data, and then talk about the deep learning part. Out of curiosity, who has seen forward propagation and backpropagation before? You raise your hand. OK. It's going to be super useful. So why did you ask me to present this, Aaron? So hopefully it'll be like watching a movie you really liked for the second time, and hopefully it will not be like when you watch a movie you liked and you realize, oh, the special effects weren't that great. So, all right, let's get going on forward propagation. Let's just start simple. Let's just start with describing what do we mean by an artificial neuron. So an artificial neuron will be essentially characterized by a few things. It will take some input x, and it will have a set of weights, which are connections between the inputs and the activation, the neuron itself. It will have a bias, and it will have an activation function. And the way we will compute the activation of a neuron is that we will first take the bias. So we're going to first compute what I call the pre-activation function. I'm noting a of x. It's going to be a bias plus a linear combination of the inputs, where each input dimension in my vector x is weighted by some weight wi. The weights wi's are just the elements, the dimensions in my weight vector w. So this sum, I can represent it as vector operations by as b plus the dot product between my weight vector w and my input x. So that's how I get my pre-activation. And then to actually get the activation, and sometimes we'll refer as the output of a neuron, will just be some nonlinear function, g, which is our activation function, applied on the pre-activation. So if I unroll everything, it's that equation here. And so this is kind of a visual illustration of what a neuron is. And often the bias will just represent it as actually the weight of on a unit that is constant and equal to 1. So that's another way of representing that full sum as just multiplying an extended vector with w and b added appended to that vector. So okay, what kind of functions can we represent with an artificial neuron? So we can just plot the output of some neuron. If we want to do that in 2 dimensions, because that's easier to visualize. So here we have one axis where I have the first dimension of some input, and here second axis of second axis for the second dimension, my input. And here this is just the output or the activation of my neuron. And so typically what we have is that in some region of the input space, what I'll have is essentially a flat and small value. And then as I move along in the direction of the vector W, eventually the activation starts increasing. That's what we typically get. And often we can even get a kind of ridge that separates two regions. So this is the kind of function you can represent. And so the bias B will determine where along vector W that ridge will be. And the range of the values taken by the activation of a neuron is going to be determined by the choice of my activation function. So that's a single neuron. Oh, and please do interrupt me at any point during the presentation if you have questions. I'll be happy to make this more interactive and discuss some of the details. So I talked about activation functions. What are the choices? One would be to essentially have no activation function. So I have a linear neuron. This just means that the activation function on my preactivation is just the preactivation itself. That's not very interesting. We often have sigmoid units. You have actually seen that in Doina's talk earlier this morning. So the sigmoid function has the property that it essentially squashes the preactivation between 0 and 1, as you can see here. So this axis is the preactivation, and that's the activation of the neuron. You can see it's squashed between 0 and 1. It's always positive, it is bounded, and it's strictly increasing. So the higher the preactivation, the higher the activation. And the actual mathematical formula for the sigmoid is this here. It's 1 over 1 plus the exponential of the negative preactivation. Another popular choice is the tanh, or hyperbolic tangent function. In this case, mainly what changes, it's quite similar to a sigmoid function, but instead its activation ranges between -1 and 1. And so you have this somewhat more complicated formula, which is the exponential of the preactivation minus the exponential of minus the preactivation, divided by the exponential of the preactivation plus the exponential of the negative preactivation. This is one way of computing it. You could multiply the numerator and the denominator by the exponential of the activation, the exponential of A. And then you would get this formula, which is slightly more interesting just because here we only have to compute one exponential, the exponential of twice the preactivation. And the exponential is more computationally expensive to compute, so that can be a more convenient form computationally. And then finally, probably right now, the most popular activation function is the rectified linear activation function. We often refer to those as the this is painful, ReLU, okay, for rectified linear unit. So if you see this in papers, this is referring to the usage of this activation function, the rectified linear activation function. It is bounded below by 0, but it is not upper bounded. It's also increasing, not strictly though, because here it's not. It's actually flat. That's a mistake. And then in practice, it will tend to give, when you train a neural net with ReLU units, it will tend to give you sparse activities, which is a property we observe empirically. And the function itself is simply the maximum between 0 and the preactivation. So if the preactivation is larger than 0, you get a linear function. But if it's below 0, you get a flat 0 output, 0 activation. All right? Any questions on that? OK. So what is the capacity of a single neuron? What kind of things can we achieve and represent using a single neuron? So we've seen this picture already. And you can, just looking at this, already see that it seems we are able to represent linear decision boundaries, so perform linear classification. So indeed, if we think of a single neuron and we use the sigmoid activation function, one thing we could do, if we wanted to take the probabilistic approach of classifiers that Doina described, is to think of the activation of that neuron as representing what is the probability that for some given input x, the label associated with my input is 1. So think of in my notation, I'm going to assume sometimes a binary classification problem, in which case the positive class is 1 and the negative class is going to be 0. So this actually corresponds to the model behind logistic regression that Doina presented. And so if we wanted to make a prediction, that is, assign a label to some given input, we would just compute our activation of the neuron, linear transformation, followed by sigmoid, and then we would threshold at 0.5. Why? Well, if that represents the model's predictive distribution over the label y, if its value is higher than 0.5, it means it thinks it's more likely that it belongs to the class 1 than the class 0. And so that's how you would get a classifier performing classification using a single neuron. So one can easily see that you would essentially be drawing a line in your input space between the positives and the negatives. So what kind of functions can we represent? So I'm going to use a very simple example of Boolean functions, which is a classic example for explaining why we want more than just a single artificial neuron. So it's also, even though it's simple, it's kind of interesting in the sense that if we would like to use neural nets to perform some kind of logical reasoning, we would probably want such functions, such neural nets, to be able to represent certain, at least simple Boolean operations. So I'm representing 3 different Boolean operations. So here, true is represented by 1 and false by 0. So if we have the OR function, the OR function would output true or 1 if any of its input, x1 and x2, is equal to 1. So in this case, so the triangles would be the positive class. So we can see if either this dimension or that dimension is equal to 1, we are in the positive class, an output of 1. And otherwise, if both are 0, we get a 0. So we can see that in this case, it is easy to draw a line that separates all the positives from the negatives. So we can represent that with a single neuron. Another function is the n function. Here I'm showing the n function on the negative of the first argument and the second argument. So in this case, n will be equal to 1 or true only if both arguments are 1. So it means that x1, since I'm taking its negative, needs to be 0. And then x2 needs to be 1. So that's why I have a positive example here. And all the others, either one is going to be 0. So I get the negative class. And again, in this situation, I can easily chop the space using a line into the positives and the negatives. And same thing for n, where I would apply the negative on another argument. So all of these functions I can represent with a single neuron. However, if I take a slightly more complicated, but really not that complicated function, the XOR function, which is equal to 1, outputs true if either 1 is equal to true and the other false, or vice versa. So in this case, this would be a positive example, 0, 1, and 1, 0 would be the other with an output of 1. And any other combinations, 2 1s or 2 0s, would be correspond to an output of false or 0. So we can see that in this situation, we cannot draw a line and separate perfectly all the positives on one side and all the negatives on the other if I was to draw a decision boundary that's linear. This is actually kind of a famous example. It was shown. It was used historically in the Perceptron's book to show that a single neuron has some limitations. However, much like Doina described, maybe I can transform my input space into another representation and then get a problem that's simpler, and in this case can be separated by a single neuron, by a linear decision boundary. So what I'm showing here on this side is what if I take my input space and instead now the 2 dimensions with which I'm going to draw my inputs, my examples. The first one is going to be the n over the negative of the first dimension and x2. And the second dimension is going to be the n of the first dimension and the negative of x2. So in this case, this example here, 0, 0, would have an end for both this n and this n be 0. So it would actually map to this point here. And actually, this point also, if we run through the calculation of both ends here, will also wrap into the same point. And we can go through the derivations and find out that for both these points, they also lie essentially at the same place. So in this case, I can actually draw now a line between the positives and negatives. And the thing to notice here is that the function that I've used to now draw my data differently are these 2 n functions that I shown before that I could actually represent with a single neuron. So what this example suggests is that if I first compute a few set of neurons, and then I have some output neuron that is connected to these intermediate neurons, then now I can start modeling nonlinear decision boundaries. In this case, I can actually model this function here, the XOR function. And so that is at the core, like why we are interested in neural nets. Why are neural nets interesting is that they allow us to go beyond linear classifiers and actually model nonlinear decision boundaries. Any questions so far? All right, so that brings us to multi-layer neural net. I'm going to start simply with a single hidden layer neural network. So in this case, what this means is that between the input and the output, I'm going to have a layer of what I call hidden units. Each of these units are like artificial neurons. That is, they are connected with the previous layer, the input. And they perform a linear transformation of the input and then apply some activation function. Okay? So you're seeing here essentially a slightly different notation in the context of one hidden layer neural net. But we see the same form for the pre-activation. It's a bias. So in this notation, I'm using the exponent to index the layer. So this is B1 because this is a bias for the units at the first hidden layer. And then this index I is to indicate that this is the bias for the ith layer, ith unit in the first hidden layer. And so I'm going to take that bias to get my pre-activation plus summing over the contribution of all the input units, so all the units in the previous layer, weighted by the corresponding weight of the connection between the jth input and the ith hidden unit, the one for which I'm showing the computation of the pre-activation. And again here, this matrix W, which contains all the weights between all pairs of hidden unit and input unit, I'm storing them into this matrix W1 that I'm using an exponent to index to refer again to the first hidden layer. And I can actually write the computation of all pre-activations of all units in the first hidden layer in vector form. So I can just take the bias vector, B1. And then as you've seen here, what this operation corresponds to effectively is to take the vector x and multiply it by the row, the ith row, of my matrix W. So if I just take the product of the x multiplying on the right with my matrix W, what I'll end up doing is for each row, I'm going to do a dot product between x and the corresponding row of weights, which means that I get all the contributions to the pre-activation for all hidden units. So to sum up, my pre-activation is just this vector-valued linear transformation on my previous layer, the input layer x. And then, as for usual, for regular units, I get my hidden layer activation by applying my choice of activation function g over my vector, applying it element-wise. And then finally, to get my output, imagine I'm performing binary classification. So at the output, I would like a neuron between 0 and 1 that gives me the probability belonging to the positive class. Well, I'm again going to take a bias, so B2 now, because I'm at the second layers, which is the output layer. And I'm going to multiply by some weight vector connecting my output unit with all the hidden units that I'm noting W2, multiplied by the activation of the first hidden layer, which is H1. So here I should probably have a 1 here. So that's for a single layer neural network. Any questions on the notation or anything related to this slide? OK. So I described the case of binary classification. More generally, and more commonly, we would be interested in classifying into multiple class, so performing multi-class classification. So in this case, what it means is that an input might belong to one out of C, capital C different classes. And so if I wanted to do this, I would like to represent, with my neural net, some probability distribution over all the classes. So a conditional distribution of my input x belonging to one of the capital C different classes. So I'm noting that mathematically as the probability of y, my label y, being equal to some small c, which is a choice between 0 and c minus 1. Or actually, I'm indexing from 1 to capital C here. So one way to get these probabilities is essentially have an output layer that is always positive and whose activations sum to 1. And there's a very simple way of achieving this with what is known as the softmax activation function. All that it does is that it takes the pre-activation vector at my output layer. So these are the A's at the output layer. And then I'm going to take the exponential on each dimension. And finally, I'm going to divide each dimension by the sum of the exponentiated pre-activations. So you can see that writing it this way, all my dimensions is going to be normalized. That is, if I was to sum over all the values in that vector, because I've explicitly divided each dimension by that sum, I'm going to get a sum that is equal to 1. So because of this, I can interpret the output as a multinomial distribution over my input x belonging to one out of the c different classes. And if I wanted to actually perform classification with a model that had a softmax output, I would just look at which unit has the highest activation. That is, according to my neural net, what is the class that has the highest probability given my input x? And that's how I would perform. So we can go from one hidden layer to multiple hidden layers. So I'm just extending my notation here, where now I'm using k as some arbitrary hidden layer within my neural net. I'm going to use capital L as the number of hidden layers. So in this case, pre-activation and some layer k is just going to be a linear transformation of my previous layer. So in my notation, to make this equation work, I'm going to assume that h0 of x is actually the input. So the layer below the first hidden layer is the input. And so now the pre-activation is just this linear transformation, taking my weight matrix, multiplying it by the activation of the layer below, plus some bias. And finally, I'm going to get the hidden layer activation by applying my activation function. And I do the same thing for the output, but typically for the output layer, I'm going to use a different activation function. And as I've described, if I'm performing multi-class classification, I'm going to use the softmax for the activation function at the output. And for the hidden layers, I might use the sigmoid. I might use a tanh. Quite frequently, we'll actually use the ReLU, the rectified linear activation function. OK, any questions so far with any of this? Yes?
Kind of notational thing. So
yes.
we were showing the softmax equation.
Yeah.
There, we're describing it as a row vector. Is the transpose just to get it to be vector?
Oh, yeah, excellent point. So my assumption when I'm writing vectors is that they are column vectors. And so because if I write it this way, it suggests that it's a row vector. The transpose here is to emphasize that I'm taking that row vector and transposing it. So by default, if you see a vector notation, and that's a good point you're mentioning this. I haven't really emphasized that. So whenever I use a bold type, it's to refer, and a lowercase, it's usually to refer to a vector. If I'm using bold, but for a capital letter, it's usually going to be a matrix. And if it's italic instead of like this one here, instead of bold, that's going to be a scalar. Okay, so I'm going to try to hopefully help out understand whether we're referring to scalar of a vector. I'm going to try to stay true to that convention. That's a great point. Yes?
What's the rule of thumb for picking nonlinearity?
So the rule of thumb is use the ReLU. That tends to work really well, but I've seen examples where it turns out that the sigmoid for some reason is better, or the tanh. I think that, I don't know if Yash or Aaron has like their own rule of thumb, but typically I start with the ReLU, and then maybe I will try the sigmoid and the tanh if for some reason I'm not satisfied with the results. That would be my rule of thumb, but I don't know if, yeah. Yes?
Would you want to use different nonlinearity at different layers, or you always go with sigmoid?
I mean, I can't say that I've seen a lot of, oh, yes, thank you. So you will have to tell me that often. So the question is, should we use different activations at different layers, at different positions in the different hidden layers of a network? I haven't seen a whole lot of success in actually kind of fine-tuning the type of activations you would use at different places in a neural net. So I would say that usually that's not the biggest bang for the buck in terms of performing more experiments. There is some research on trying to make the activation function learnable in some way. And that research is interesting, but I can't say I've seen like tremendous success in terms of like improving performance in a way that's particularly meaningful.
Except for the output and some special structures like gating and
Yeah.
tension and stuff like that.
Yeah, so except for the, yeah, that's right. So except if you want to put structure in terms, for instance, there's forms of attentional mechanisms which correspond to using different types of connections between units and different forms of activations that are inspired by trying to emulate some activation, some form of processing. And in this case, I think it makes sense to reason in that space. But at the individual unit in the regular sort of tower-like, layers that are stacked, I haven't seen a whole lot of gains in trying to really tune the individual choices of units across layers. Yes?
Does it matter if the activation is differentiable? Or
Sorry?
does it matter if the activation is differentiable?
Oh yes. So we will need. So it's a yes. Is it important for the activation to be differentiable? It will be if we want to perform gradient descent, because then we will require gradients, and so we'll go through that in a bit. But if the activation function wasn't differentiable, then you need to leverage sort of more advanced principles for training, forms of reinforcement learning, for instance. So if you have stochastic units, for instance, for which you cannot backpropagate, so get a gradient through the sampling, that's an example where you use an algorithm like reinforce. So, but typically, like it's a pretty good thing to have a activation function for which you can compute gradients, because then you can do end-to-end learning with gradient descent.
Why is the best choice?
So it is differentiable at every point except the inflection point, at which we can get a subgradient, and there's some theory that suggests that doing subgradient descent, it's still fine. So in this case, that's why it's not a problem, the fact that there's no, that you don't have an exact derivative at the inflection point. But that's a good point. Yes?
What's the reason for choosing exponential in the solve? Is it just to make the derivation calculation easier, or?
Yeah, so the question is why use the exponential here? I think, yeah, that is one good motivation, the fact that when you start computing the gradients with respect to the preactivation, when you use the exponential and we use the loss, which is the log likelihood, as we'll see in a few, you get fairly simple forms of gradients. So I think that is one motivation. Yeah. Yes?
So just to piggyback off the other question about layer-wise activations is one thing, but someone asked me once, and I couldn't think of a good reason why couldn't you mix within a layer different activation functions? Is there any research that you've ever seen that actually has shown that's useful, or there's a particular reason, like mix ReLU sigmoids and tanh? I mean, because it seems like that could be a cocktail or a mix, but any particular benefit in any research where mixing it within a layer, into a layer, makes any sense?
Yeah, so the question is whether there's a benefit to maybe within a layer try to vary the types of activation functions. I don't know if Yash or Aaron have any examples, but I can't think of any that's like really compelling.
The only thing I can think of is something like max out, which you can think of as a bit of a generalization from ReLU, where we're basically putting together a bunch of piecewise linear units, right? So this is something we've done, we did a few years ago. Ian Goodfellow was the first author on that. So that's a case where they're free to learn. Like Hugo mentioned that there are a few examples of this. And you could imagine that it would learn different functions within a layer. So on average, it tends to work about the same as ReLU, sometimes a little better, sometimes a little worse. For some reason, for speech recognition, it seems to work very well. It's been our observation. But yeah.
But throwing in like non-linear and piecewise linear, the standard mix of functions, aside from being more of an engineering headed to separate out and stuff, there's no necessary
I've not
benefit.
seen any good work in that direction.
So for the video, Aaron gave an answer. It was like, yeah. He essentially said that examples like the max out is a form of learning the activation function. And to expand on this, actually, you can, because when you get the activation, you will ultimately multiply it to get the preactivation at the next layer. You're going to perform a linear operation. It could be that actually linear combinations of certain units within the layer is by itself a more sophisticated activation function. And actually, this kind of builds into what I was going to talk next, which is the capacity of neural nets. So let's move through that. So just to try to give you an intuition as to why you can get nonlinearities and what forms of nonlinearities you can potentially model with a neural net, I'm going to give you a few examples. Those are taken from Pascal Vincent's slides. So for instance, you could imagine, as we've seen before, that I could have one single neuron that represents this function here, some sort of ridge in some direction. And then I could have the same ridge but shifted by changing the bias with another unit. And then you can imagine that if I take essentially this unit and subtract that unit, I will get as a result a sort of ridge that's like a bump in this direction, going up and then going down. So this is what I was referring to, where you can take combinations within layer, just linear combinations, and effectively it's as if you're getting a more sophisticated activation function to some extent. Then you can start imagining doing this, but in multiple directions. So here you have something slightly different, which is you have a neuron that increases in one direction, and then the other neuron that starts high and then decreases. So this would just be, you would assume it would take the same weight vector, but the negative of the weight vector. And you could do that in two perpendicular directions. And then linearly combining all of these in the appropriate way, you would obtain in the original input space a bump at some place. So now you can see that, at least in 2D, with 4 units, you can get a bump, positioning a bump that gives you a high value at some very restricted area in the input space and low everywhere else. So then it's not a big stretch to start imagining that if I combine such groups of 4 units in 2D, I can now easily get fairly complicated decision boundaries where maybe I have a bump right here, and then I get a bunch of little bumps here to get also the positive class in this area, and everywhere else there's no bump. So you get like a negative in R2, and then a positive value over the threshold for classifying in the positive class in the area R1. And so you can actually formalize and use that intuition to actually show, and that was shown by Hornick in 1991, that a single hidden layer neural net with a linear output unit can approximate any continuous function arbitrarily well, as long as you give it enough hidden units. As long as the hidden layer is big enough, it is possible to by hand construct, well, it would be possible theoretically construct by hand a function that would approximate arbitrarily well some arbitrary continuous function. This result actually applies for sigmoid and tanh and many other hidden layer activation functions. And so that's a really important result. It tells us that technically, if we make the hidden layer large enough, we can pretty much model any function we want. So no matter what is the function that generated my data, I have the flexibility within the family of neural nets to potentially represent that function, to learn that function that is responsible for the data I'm seeing in my training set. Now, this result, however, doesn't tell us anything about how do we actually learn the neural net to represent that function. And so this is where we get to the learning algorithm, which I'll talk about next. Any question at this point on this first section? Good. All right. So let's talk about backprop. So I'm just going to start by formulating the learning problem, the problem conceptually of training a neural net on some data set. So what we'll do is use the paradigm of empirical risk minimization with some regularization. So in empirical risk minimization, what do? We frame the problem as follows. So I'm going to use x with the exponentiated index t to refer to the tf input in my data set. Y exponentiated t is the tf label in my data set. So f of x, as I've mentioned before, that's going to be the output of my neural net. And here I've just added a little bit of notation that makes it explicit that my neural net has parameters, and those are represented by theta. So theta would, in the context of a neural net, contain all the weights and the biases in my neural net. And I'm going to define a loss function that compares the output on my TF input with the actual true label. Okay, so it's assign a loss if my prediction isn't correct. For instance, I'm assigning too high of a probability on the wrong class. And so in empirical risk minimization, what we try to do is minimize the average loss on my training set. The average of all the losses when I'm comparing the output on the training set of my neural net with the actual true label. And also, usually we add some regularization that Doina mentioned, and weighted by some hyperparameters, some factor lambda that will control the trade-off between a lot of regularization and fitting my data well. I should say that technically speaking, when we have regularization, we don't talk about empirical risk minimization, but structural risk minimization, if you want to be precise about things. And so in this context, learning is cast as an optimization problem. Learning will correspond to taking my training set and finding this theta here, which minimizes this expression. So how do we do this? There are multiple different optimization methods, and one that's very simple and works really well in practice, and I'll expand on slightly more sophisticated versions of this, but one that works really, really well is the stochastic gradient descent procedure. So in stochastic gradient descent, I first start by initializing my parameters in some way, and we'll discuss probably after lunch about how to do that properly, and because there are certain badly constructed cases you don't want to use. And then for some number of iterations, I'm going to take out of my training set an example, so a pair of input xt and label yt. And then I'm going to look at what is the direction in which my loss would, for that example and for my regularizer, would decrease the most. In other words, I'm going to look at what is the gradient of the loss with respect to my parameter. So nabla is the gradient on this loss. And here, as an index to nabla, that is not clear. And as an index to nabla, I'm using the parameter with respect to which I'm taking the derivatives. And I'm also, so because I have the sum of the loss and the weighted regularizer, the gradient on all of that is just the sum of the gradients. So I also get lambda times my gradient of my regularizer. And so the gradient tells me in which direction the loss and regularization would increase the most. I'm going to go in the opposite direction to take a step in the direction in which it would decrease the most. And I'm going to take a step in that direction. So that direction, I'm calling it delta here. I'm going to multiply by a step size alpha. We'll usually refer to the alpha as the learning rate. And I'm going to move in that direction. That is, I take my current value of my parameters, and I just added alpha times my direction. So that gives me my new parameter. And I'm going to repeat this several times. Okay? So that's effectively stochastic gradient descent. It is gradient descent because, as you can see, I'm computing gradient, and I'm going in the descent direction for that gradient. And it is stochastic because, unlike what Doine have shown, where you would take the whole objective, the whole average of losses in your training set, and take the gradient with respect to the whole average, here I'm actually taking the gradient for a single example that is stochastically drawn from the training set. And actually, in practice, often we linearly iterate over the examples. And we usually, probably inaccurately, usually refer to that as stochastic gradient descent. So if I want to apply this general procedure, here there's nothing that particularly refers to a neural net beyond the fact that I've said theta would be the weights and the biases. But if you have some function f, this is essentially really just an optimization procedure. So what I need to do here in the context of my neural net is to specify what is the loss function, specify a procedure that is as efficient as possible for computing the gradient of the loss with respect to the parameters. And I need to specify a regularizer, and from the regularizer, get a gradient on that. And also, I will need to specify how to initialize my parameters. So before the lunch break, I'll actually essentially focus on what is the loss function and how to get the gradients of the loss with respect to my parameters, which is essentially the backpropagation algorithm. So if there are no questions, let's move to the loss function. So as I've hinted, we might actually want to, yes. Oh, yes, sorry.
Small detail, because you
Yep.
mentioned that you don't call empirical loss minimization or empirical risk minimization, that you call it structural when you add any regularizer like L1, L2. So that means even when you're doing like any of these other alternative forms like dropout or structural priors or anything which we call regularization of some form, we're always doing that structural risk.
I don't, oh yes, repeating the question. This is going to be painful. I shouldn't say that. Ask questions. Don't worry about me. So the question is whether if we use other forms of regularization like dropout or unsupervised pre-training, are we then in the family of, would we refer to that as structural risk minimization as opposed to empirical risk minimization? I believe so. I'm actually not sure what is the official, if you actually have to have this explicit regularization term in what you are optimizing. I believe that might be true, and for dropout, it's not necessarily for deep neural nets explicit what the regularization term is. So I'm actually not sure. That's a good question. OK, so the loss function. So as I said, we're going to use the values of the units at the output layer as a predictive distribution over what is the class C, or I guess Y. So the Cth unit and my output layer is going to be interpreted as the probability that my input X belongs to class C. That is the model probability as predicted by my model. So what we could do, one form of learning, would be to do maximum likelihood. So that is, try to maximize the probabilities of the assigned labeled in my training set, Y, for each of my input examples, X. Because all the math is nicer, numerically it's nicer, instead of maximizing the probabilities, we're going to maximize the log probabilities. And because I've just framed everything into a minimization problem, we're going to minimize the negative of the log probabilities. So my loss function is just going to be minus the log of the value of the yth yth unit in my output layer f of x. You can also write this as summing over all possible classes C, and I check whether my iterator C is equal to the true label Y. And then if so, this is equal to 1. This is just the indicator function. Otherwise, it's 0. And so when it is equal to 1, I'm effectively going to have this term be present in the sum, which is just the log the probability of that class C. And the reason I write it in this way, where you have a minus here, is that sometimes you will see people referring as the loss used for training as a cross entropy. And in this form, it's more explicit that you have a cross entropy. It's the cross entropy between this distribution here, that's the output layer of my network, and a multinomial distribution that puts probability 1 on the correct label and 0 everywhere else. Okay? So that's why sometimes we also refer to this as the cross entropy. So let's start computing gradients. So we're going to look at what is the gradient of the loss with respect to computations at the output layer. And we'll slowly make our way towards the parameters. So if I wanted, so the gradient is just a vector of partial derivatives. I find it more convenient to start by computing the derivatives and then show that from the expression, the generic expression for the derivatives will get an expression for a vectorial expression for the full gradient. So if I wanted the derivative of minus the log of the probability of the correct class with respect to my output for the Cth class, well, the derivative of minus the log, that's going to be minus 1 divided by the argument of the log. That's the probability of the correct class under my model. And the derivative of f of xy with respect to f of xc, well, that's going to be 0 if c and y are different. So if c is a different class than the correct class y, it's going to be 0. And otherwise, that's going to be 1. So that's why this 1 here is actually now an indicator function of whether y is equal to c. Now, if I want to just take that expression and construct a vector corresponding to the gradient of the loss with respect to all of my outputs, what I'm going to get is, well, all of the terms for all values of c is I'm always have this minus 1 divided by f of xy. And then the only thing that changes with c is this term here, right? And so I have this vector of whether y is equal to the first term. So here, for some reason, I switch from classes 1 to c to 0 to c minus 1. Just make sure everyone's following, so keep you on your feet. So if y is equal to 0, y is equal to 1, and so on up to c minus 1. And actually, this vector, I'm going to note it down as e of y, or I'm going to refer to it as the one-hot vector for label y. So that's just a vector that has a bunch of zeros, except for one 1, which is at the dimension corresponding to, in this case, the index y. Okay, so that's a notation I'm going to use throughout. So the gradient with respect to the output is just the minus the one-hot vector divided by, so scaled by 1 over the probability of the correct class under my model. I can also go a bit deeper in my network and ask, what is now the gradient with respect to the pre-activation at the output layer? Now, so as we will show in a few, it actually has a very simple expression. You actually seen this expression in Doina's talk. It's going to be simply minus whether my output unit C matches the correct label minus what is the current output, so after the activation function, for the unit C. Okay? And so if we put all of this together to get a vector, all we get is minus the one hot vector minus the output. So you can see that this gradient is essentially comparing what is the ideal output, which would be a probability of 1 for only the correct class, and everything 0, and it's comparing that with the current output of the model. Okay? So this, I haven't shown the derivation of this. I will do it with you because I find it instructive, and because it used to be that we did that in our neural nets class, so you're going to suffer through this if you haven't yet. So I'm computing the derivative of my loss minus the log of the probability of the correct class with respect to the pre-activation at my output layer. So this is why I have A of L plus 1. L plus 1 is the index of the output layer with respect to some arbitrary output C. So I've already shown that the derivative of minus the log of f of xy, that's going to be minus 1 over f of xy because of the derivative of the log. And then times, using the chain rule, derivative of f of xy with respect to the pre-activation at the output neuron C. Next, I'm going to write what exactly is f of xy. Well, that's actually the yf component. Once I've applied the softmax activation function over my pre-activation vector at the output layer. Okay? So this allows me to expose now the dependency of f of xy with respect to the pre-activations at my output layer. Okay, next, I'm going to write what the softmax is. Here, notice that the softmax on over vector is a vector. So here I'm indexing the yf component. So what I'm effectively going to get is the exponential of the yf pre-activation at my output normalized. So divided by the sum of the exponentiated pre-activations across the layer. So all I've done here is just take that expression, replace it with that, and take that expression and replace it with this. Now I'm going to use what is the formula where we're taking a derivation, so a gradient, with respect to a ratio of two functions of some x that we're doing the derivation with respect to. So in this case, my function g is the numerator here. My function h in that identity here is this sum over all classes of the exponentiated pre-activations. So what is the expression? I'm going to take the derivative of g of x with respect to x times 1 over my denominator. So 1 over my denominator is just this part here. And here I'm multiplying by the derivative with respect of g of x. G of x is this with respect to my pre-activation. And the same thing here. So g of x is right here. The square of h of x, that's the square of my normalization constant. And then multiply by the derivative of the denominator h of x, which is this sum of exponentiated terms. So I take the derivative of this expression with respect to my pre-activation at node C. All right, so if I take that derivative here with respect to the exponential of the pre-activation at the label y, well, if c and y are different, that's going to be 0 because those are two different numbers, two different pre-activations. So this is why I have the indicator function checking whether y is equal to 1. If it's not, it's going to be 0 times something, so the expression is going to be 0. And then if I take, and then otherwise, if y is equal to c, the derivative of the exponential is the exponential. So this is why I recover the exponential of the pre-activation at the correct label y. And now I'm going to compute this derivative here. So I'm taking a derivative of a sum, so that's the sum of the derivatives. And since all of the terms here, there's only one, so notice that this is a sum over all possible classes, which I'm noting as C prime to make it different from C, which is the unit with respect to which I'm taking the derivative. So in this sum, all the elements are not going to be dependent on the CF unit, except for when C prime is equal to C. And then when it is, the derivative of the exponential is the exponential. So ultimately, this whole derivative here simplifies to just the exponential of the pre-activation for node C. Next, I'm going to notice that this divided by this normalization constant is just the yth element of the softmax of my pre-activations. That's just the definition of the softmax here for dimension y. And similarly, this term here and this term here, so you can see I've taken the square here and I separated it into two terms. So I have one term which is the numerator where I get the exponential for the correct label, and here it's the exponential for the label for the node C, which is the node for which I'm computing the derivative. So both of these are softmaxes, but one is for the yth output and the other one is for the cth output. And then finally, well, to simplify further, the softmax of the pre-activation, that's f of x. So I'm replacing all the softmaxes here by f of x. And this allows me to cancel this with these terms here. And so ultimately, what do I get? Minus my identity function minus the function, the cth output of my model. This might be a good time to say my slides on the website. So if you actually want to go through this after or as we're going through and going back, the slides are in the speaker section. Yes. So everything simplifies. It might have seemed surprising, just to sum up, that the derivative of the yf output now depends on some other pre-activations for some other unit, and this is only because of the activation of the normalization constant. This is only because in the softmax I have this term here. This is why before when I was looking at the gradient with respect to the output, I had something very simple to derive, as here is a bit more complicated because of this normalization constant. Okay, so far I've went from the loss and I obtained the gradient with respect to the pre-activation. Now again, I'm going to try to go a bit deeper. Now you might have noticed that this is getting a little bit complicated. So if I was to write the whole expression of the loss with respect to each of my parameters and went through all the derivation, that would be a lot of work. So what it will do instead is exploit the chain rule. So the chain rule will allow us to use previous calculations, previously derived expressions, to get an expression for a gradient of things deeper in the network. So what the chain rule says is that if I have some function p that depends on some argument a, and I want to get the derivative of that function p with respect to my argument a, and imagine also that my function p is actually completely computable from a set of intermediate results that each depend on a. And these intermediate results, I'm going to call them qi. Well, in this case, the derivative of p of a with respect to a is the sum over all intermediate computations of the multiplication between what is the derivative of p of a with respect to my ith intermediate result times what is the derivative of qi, my ith intermediate result, with respect to a. So you can see that this result is applicable in the context of a neural net. If I want the gradient on the activation at this unit here, well, if I've computed the gradient with respect to the pre-activations here, we can see that the loss directly only depends on all the pre-activations computed here. So then the only bit that is missing is what is then the gradient or the derivative of these intermediate results with respect to my quantity, which in our next stage is going to be the activation at the layer below. So that is what we'll be invoking here for performing our derivations. So if you want the derivative of my loss function, now with respect to the jth unit at some hidden layer k, any hidden layer k, well, I'll invoke the chain rule. And by writing it as it's just going to be the sum over the derivative of my loss function here with respect to all pre-activations I for all the units I at the layer above. So with respect to the pre-activation at the layer above. That's why I have a k plus 1 here. And I'm going to multiply this by what is the derivative of the pre-activation at the layer above, k plus 1, for the ith unit with respect to the activation at the layer k for the jth unit. Okay, so just applying the chain rule here. And so I'm going to assume that I've computed this already. And as we shown before, we already did compute the gradient of the pre-activation at the output layer. And now the only bit that is missing is this part here. What is the derivative of my pre-activation at the layer above with respect to some activation of some unit in the layer below? Well, pre-activation is quite simple. It's just a linear transformation. So I'm just taking a bias plus the sum of all the weighted contributions of all units in the layer below. So if I'm taking the derivative with respect to the jth unit, so the derivative with respect to the pre-activation, well, with respect to the bias, that's 0, because the bias is it doesn't depend on the activation at the layer below. And then I have a sum over all units j of the weight times the activation. And so all of these terms here, the derivative with respect to a specific unit is going to be 0 if it's not that unit. So if this j here is not the same j as here. And when it is, well, you have a scalar times my variable with respect to which I'm taking the derivative. So that's just going to be the scalar. So ultimately, this will simplify where this sum goes away. And then I remove this. So I get the scalar in front of my variable with respect to which I'm taking the derivative. So this is why this whole term here becomes just the weight between the ith unit at the layer above and the jth unit at the layer k. And one other way of writing this, I have a sum over all units I in my layer k of the weighted partial derivative with respect to the pre-activation at the layer k plus 1. So one thing I could do is actually consider the whole gradient. So the whole gradient of with respect to the pre-activations at layer k, and multiply that. See, I'm indexing with respect to I, so I'm indexing over rows. So multiplying this by the jth column of my matrix W. If I want to write, instead of having explicit sum, actually write this in linear algebra. So I can just write this instead as the gradient of my loss with respect to my pre-activations at layer k plus 1 multiplied by the jth column of my matrix W k plus 1. So here the notation I'm using is I'm using this dot to refer to all rows at the column j. And so because of this, you can think of it as slicing a matrix. So I'm taking all rows at the specific column. So then this would be a column vector. And so to have it become a row vector that I can multiply with this column vector, this is why I'm taking the transpose right here. Okay. So that gives me the derivative with respect to some activation of some unit at layer k. And now if I wanted the full gradient, so the vector of all derivatives with respect to all activations at layer k for my loss, well, all I need to do is essentially perform this operation here, but for all columns j. Well, I get that simply by taking my gradient of the pre-activations at the layer above and multiplying that by the full matrix transpose. Okay, then I'm going to be multiplying by each of the columns and get the vector of all the derivatives. So ultimately, after doing all these derivations, going from pre-activation gradient to activation gradient at the layer below is a very simple operation. Just take the above pre-activation gradients and multiply by the transpose of the weight matrix. And now if I wanted to get at the second stage, again, my gradients with respect to the pre-activation at this same layer k. So I will again evoke the chain rule. So in this case, the pre-activation and the activation in one layer are, so the activation of one unit only depends on the pre-activation of that same unit. Unlike at the output. At the output, it's not the case. There are dependencies because of the normalization constant. But here I'm going to assume that I'm using an activation function like the sigmoid or the tanh or the relu, in which case you just have an element-wise computation. So there's no normalization within the layer. So in this case, the derivative of my loss with respect to my pre-activation for the jth unit at layer k, well, that's going to be the derivative of my loss with respect to the activation of that unit, hk, times what is the derivative of the activation of that unit with respect to its pre-activation. And what is this term here? Well, that's just the derivative of my choice of activation function, g prime. Okay. And now if I want to do this, so this is again the partial derivative for a single unit j. If I want to get the gradient, so the vector of all partial derivatives, all I need to do is take each individual I just need to take my gradient, my full gradient, so the vector of all partial derivatives with respect to the activation of all units. And I just do an element-wise multiplication with its corresponding derivative of the activation function. So this vector here, that's just going to be the vector where the first dimension, that's the derivative of the activation function for the first unit, and then the second unit, and then the third unit, and so on. I just pack this into a single vector. And this symbol here I use to represent the element-wise multiplication. So again, computationally, it's not a complicated operations to do. You take your vector, you construct this other vector of the derivative of the activation function, and you do an element-wise multiplication. And that's it. You now went from activation gradients to pre-activation gradient. So I mentioned the, I don't know if there are questions at this point on any other notation, or, and then a few, we'll just wrap everything into a single algorithm. So I mentioned using this derivative here. I'll just show very quickly what is the derivative of the different choices of activation functions. I mentioned the use of possibly the linear activation function, so essentially no nonlinearity. So essentially the output of that activation is just its input, its pre-activation. Well, you can see that the slope of that activation function, that's just 1, so that's a very simple derivative. For the sigmoid function, I won't show the derivation here, but you can show that it is pretty simple to compute also. It will just be the output of the sigmoid multiplied by 1 minus the output of the sigmoid. Okay? And so we can see here that what this implies is that the slope from this expression is going to be 0 if either GA is close to 1, because in this case I'm going to have 1 minus 1, so that's going to be 0, or if GA is close to 0. In this case I'm going to be multiplying right here by 0. And indeed you see that the slope towards where the activation is equal to 0 when the pre-activation is very negative, and towards the end where the activation is close to 1, so the pre-activation is very positive, you can see that the slope is indeed converging to be flat, to have a derivative of 0. And one thing that this implies also is that, remember that when I'm performing backpropagation, I'm going to do this element-wise multiplication with the gradient that I'm getting from above. So if I do this, it means that a lot of these gradients, if I'm at a saturation point, I'm going to multiply by 0, or something close to 0. And that's a known issue in neural nets, which you'll see discussed. I'll say a few words about that later on this afternoon. And probably, I suspect Joshua will talk about that in the context of LSTMs and RNNs in general. But that means that whenever you're at a saturation point, there's no gradient passing through that unit effectively. And that's a form of issue you can encounter when you are, even in practice, training neural nets. I'll say a few more words about that and trying to avoid these situations this afternoon. If I look at what is the partial derivative of the tanh function, it is, again, we can show that this is this very simple expression, 1 minus the value of the tanh squared. So again, you can see that if you're close to 1 or 1 saturation point, you're going to get 1 minus 1 squared, so essentially 1. So you're going to get a derivative of 0. So again, this formula, you can see intuitively fits with this function here. And finally, for the rectified linear activation function, super simple gradient, it is simply 1 if the pre-activation is positive, because it's a linear function, and then it's otherwise 0 if the pre-activation is negative. So this is represented by this here, the identity function of whether the pre-activation is larger than 0. Okay. Again, another very simple thing to compute, and then you can use that to backpropagate through the activation function. Any questions on this? Okay. So all we've done so far is get the gradients with respect to activations and pre-activations. Now we finally need our gradients with respect to our parameters, because those are the parameters that we will be updating with a gradient step. So let's do that now. Say I want to get the gradient, or start with the derivative, the partial derivative of my loss with respect to the connection between the ith unit in layer k and the jth unit in the layer below. I can again use the chain rule. So I can write it as the derivative with respect to my loss, with respect to the ith pre-activation at my layer k, times what is the derivative of this pre-activation at layer k for the ith unit with respect to my weight, the weight between unit I at layer k and unit j at layer below, layer k minus 1. And again, because this pre-activation function is just a linear transformation, computing that derivative is very simple. So the bias does not depend on the weight, so this goes away. And then this whole sum here, there's only the term involving the unit j with respect to which I'm computing the derivative that matters. And in this case, all you will get is, so the derivative of the weight multiplied by the activation, well, that's just going to be the activation itself. And so this term here is just replaced by what is the gf activation in my hidden layer k minus 1. And so now if I wanted to take all these partial derivatives and put them into gradient format, so get the full matrix of all the partial derivatives, so I can see that the element at row I and column j is essentially just, well, take the partial derivative for the kth pre-activation, the pre-activation at layer k with respect to the ith unit, times the activation of the jth unit at layer k minus 1. So one thing to obtain this is to just take the gradient vector of the pre-activation at layer k, that's a column vector, and then do an outer product, or essentially take the product with the row vector of the activations at layer k minus 1. So that means that the entry at the row I and the column j is just going to be the ith element of this vector times the jth element of that vector. And that is exactly the expression that I have here, the ith element of that vector and the jth element of the activation at layer k minus 1. So really getting the gradient of my full weight matrix for the kth layer is just take my pre-activation gradient and do the outer product with the activation gradient, the activation, not the gradient, the activation at the layer below. And next we can do the same thing with the bias. As we've seen, we can interpret the bias as just a weight vector on a constant unit equals to 1. So not surprisingly, we essentially get the same formula as for the weight, but instead of h here, we have 1. So we just have effectively the derivative with respect to the pre-activation. So if I wanted to just construct the full gradient for my full bias vector, it is essentially just the pre-activation gradient with respect to my full loss. Okay, just the gradient of the pre-activation. Okay, so let's put this all together and to get finally our algorithm, the algorithm that will give us, for some given example xy, what is the gradient of the loss function with respect to all my parameters. And what it will essentially do is go through all these different gradients that we've seen in order such that I can always reuse computations I've done before to get my computations that I need next. And the way we do this is we first compute what is the gradient of my loss with respect to the, we could do the activation, we'll do the pre-activation since its formula is simpler, at the output layer. So AL plus 1, that's the pre-activation at the output layer. And we've seen that the gradient of the loss for this pre-activation is just minus the one hot vector minus the output, so after the softmax. So I compute this, and I'm going to go from the output layer towards the first hidden layer. So for k from L plus 1 down to 1. And now, once I'm at the given layer k, well, I've already, so when I'm starting this iteration, I'm assuming that I've already computed the gradient of the pre-activation for that layer. So in other words, I have what is the gradient of my loss with respect to my pre-activation. So the first thing I'm going to do in my iteration is get my gradients with respect to my parameters for that layer, for layer K. Well, what is that? That's just I take my pre-activation gradient, I do the outer product with the activation of the layer below. So here in this algorithm, I assume that I've already performed the forward propagation. So I already went from X up to the output. So I've computed all the activations of all layer. I've computed my output. So this simple operation now gives me the gradient for the weights. And now if I want the gradient for the bias, that's just, as I've shown, the gradient of the loss with respect to that pre-activation at the layer K. And then next, I'm going to take the gradient on the activations and push it down to the next layer, K minus 1, so that at the next iteration, I can perform, again, the same computations to get the gradients for the layers below. So I can go from the gradient of the loss with respect to my pre-activation to get the gradient on the loss with respect to the activation at the layer below, as I said, by just taking the gradient of the pre-activations and multiplying that by the transpose of the weight matrix. Simple operation. And then next, I take what I just computed, the gradient on the activation, which is right here, and I do an element-wise multiplication with the derivative of the activation function. Again, another simple computation. And that gives me now the gradient of the loss function with respect to the pre-activation of the layer below. And then I continue my iteration. So now K becomes K minus 1. I continue like this until I reach the first hidden layer. And at the first hidden layer, you don't compute this line because this is the layer below, and there's no pre-activation at the input layer. Okay. So that is the backpropagation algorithm. As you can see, its complexity is essentially the same as doing a forward propagation. For propagation, you do computations for each layer, one after another. Backpropagation, you do a similar type of computation, but you go from the top layer and you go down. One way we can implement backprop is to consider this perspective on the forward propagation and backpropagation on neural nets. So what we can do is just represent all of these computations in the forward prop pass as a computation graph or a flow graph. So when I'm performing forward propagation, so when I'm trying to compute what is my output of my layer and then ultimately what is the loss for some given input X and some target Y, well, I need to take my input X and then I need to combine it with my parameter W and my bias B for the first hidden layer and compute my pre-activation. So that's just a linear transformation, taking X, multiplying it by W plus the bias B. Then I'm going to apply on the pre-activation an activation function that gives me the activation H. And then I'm going to get the pre-activation at the next layer, which requires me to depend on what is the weight at that layer, what are the biases at that layer. And then in this case, I just have one single hidden layer. So I already at the output. When I compute the output, for classification, I apply the softmax. And once I've done the softmax, I can finally compute my loss, which is the negative log of the value of the unit for the correct class. So a nice way to implement the forward propagation is to just have essentially objects that correspond to each of these boxes, and that makes the particular computation associated with these boxes. So this here would just be an object that does a linear transformation given some input X and a weight and bias that parameterizes this linear transformation. This box here would be whatever activation function I've used. Maybe I have an object that's for the sigmoid, maybe I have an object for the tanh, maybe an object for the ReLU. And here I can reuse that same object that did the linear transformation, but here instead it's going to be instantiated to use the weight matrix W and the bias B, and so on. So that would be one way of sort of structuring your code when implementing the forward pass. And what's great is that if you represent everything in this way, you can actually fairly simply, at least in terms of organization of your code, get a computation of your gradients. What you can do is then also take your objects that do these different operations and have them not just have, like, say, a function that does the forward propagation, where the forward propagation takes essentially the children of these elements and computes the activation, but the backprop also, which would just take what is the gradient of the loss with respect to myself, assuming that I'm obtaining this by the node that is following in the follow graph, in the flow graph, sorry. And then take that gradient and then push what is the gradient then for all of the arguments of the forward prop function. So specifically, when you do the forward pass, you would just follow these arrows here and computing the loss up to here. And then when you're performing backpropagation, you would just call backprop, but in the opposite order. Say taking, OK, so initially you would compute what is the gradient of the loss with respect to the loss itself, well, that's just 1. Now you would call backprop on this box here, saying that, well, the loss with respect to the loss is just 1. And then ask this box to pass in here what is the gradient of this loss with respect to the output f of x. And then you could call backprop on this guy here, which would then pass what is the gradient of the loss with respect to the arguments of f of x, which is a2 here, the preactivation. And then continue calling backprop in this opposite order here. So what is nice also about structuring your code like this is that you can essentially, it is very modular. You can, construct arbitrary types of architectures with all of these components fitting into one another and get for free the backpropagation algorithm from it. And there's a lot of different libraries that effectively do this type of what is known as automatic differentiation. What I've essentially described, having objects that have a forward pass and a backprop pass function, is essentially how Torch works. Then there are slightly more sophisticated approaches and libraries that instead of essentially have these objects in this way will actually give you a functional form of performing all of these operations. Theano works like this. There's Torch Autograd that works like this. TensorFlow works like this. And thankfully this week you'll get to see how they each differ and how they implement these notions of automatic differentiation. So this means to say that all these derivations that I've done in practice, technically you never have to do all of them. You do need, however, to do it if you want to implement a new module for which for some reason your library doesn't support. And in this case, you need to be familiar with how to actually compute that transformation, and also be able to derive and implement how to get the gradient of the arguments of that transformation, of the output of that transformation with respect to its argument. And that is, common skill that you have to develop if you want to apply and perform research in neural network. Any question on this part? Yes. Right, so how do people handle loops? That was the question. I almost got the warning. You'll hear more about this when you see the tutorial on Torch and Theano and TensorFlow. For Theano, it is handled with the scan operation. Torch Autograd has a different way of doing it, where you can actually just write your for loop, and it will essentially construct a tape that corresponds essentially to these operations, and then go towards the tape, through the tape backwards. Alex Wishko will describe that a bit more in the Torch tutorial. And I think TensorFlow has or will have a version of scan at some point that I'm less familiar with. But this will be, I think, covered in the practical tutorials. And you can explicitly, that's a good point. So Yashua mentions you can also just explicitly unfold in time the for loop, which is another way of doing it. Other questions? Yes. Yes.
Automatic differentiation libraries dealing with subgradients, for instance, with ReLU?
Yeah. So if they usually, one approach is to have essentially these components that correspond to computing the forward pass for the ReLU, and then within that component, you also define how you compute gradients, and then it's within that component that you will make the assumption. For instance, here, what I've sort of barely mentioned is that for the point at 0, I was assuming I'll use the gradient or the derivative to be set to 0. And that you would implement that within that component for the bprop method or the backprop pass. Yes?
In terms of implementation of the automatic differentiation framework, you were mentioning Theano, which does a functional form, and this was more of a modular, but you're still building a computation, right?
Yeah.
Has there been oftentimes an implementation engineering standpoint, it's just much faster to do it from like a functional form versus this, or is there, here you're doing more objects, object-oriented because I know everyone compares all the time benchmarks,
Mhm.
Torch, Theano, TensorFlow, but the fundamental idea, which is faster in practice in terms of hardware.
Yeah. I guess the question is, amongst all these different packages, Theano, Torch Autograph, TensorFlow, which one is faster and why, I guess? Or in which cases? I mean, so just maybe to not take too much time, I would prefer, pushing that question when you see the practicals, because I think this is a fairly sophisticated, it requires a sophisticated answer and understanding the specifics of each case. I can say from my limited knowledge, which is mostly focused around Torch and Torch Autograph, is that Torch Autograph in particular will be pretty convenient when you have a computation graph that tends to vary a lot for a given input, whereas I think Theano and TensorFlow deals with that a bit less well. Torch Autograph will have a certain overhead in certain situations, however, that Theano will not have, or TensorFlow will not have. I don't know if this will be covered later this week. But those are thanks to, this is, I think, partly why you have all of these different presentations this week, is that there's no one single package for every situation, at least as we speak right now, I would argue. And it's good to know all these different approaches, because behind the scene, they are sometimes substantially different. And there's a whole literature on automatic differentiation that actually goes much beyond what is currently implemented in some of these packages. And I suspect in the future years of research and developments in deep learning, we'll see us taking more and more advantage of some of these tricks.
Well, I could add something, which is that if you do symbolic differentiation or dramatic differentiation, then in principle you can, and it is done in Theano, once you've done the differentiation, what you have is a symbolic graph that describes the computation. So now you can apply compiler tricks to make that computation more efficient or more numerically more stable. Whereas if you have something like the standard Torch way, where you're just going to concatenate the backprops of each module, you can't do that. Also, there are some computations, derivative computations, that you will be able to do with things like Theano. For example, imagine second derivatives. You apply twice the first derivative. You can't do that with the Torch approach. But of course, these are a bit exotic. In practice, in terms of speed, it's more or less the same thing.
Yeah. Other questions? Whoops. Okay. I worked hard on this animation, so let's look at it again. Okay. All right. And that's it. So yeah. So later on, finish the training algorithm and talk about deep learning after lunch. Thank you.